Right, the 5 triangle congruence conditions that allow us to establish that 2 triangles must be congruent. There are 5 of them, and the very first one that we looked at in class was, I believe, angle side angle. And the way that we established this is actually a fact, right? We verified this. It was more than just a congruence condition. We proved it in class, and the thinking was that we were able to show that if you have 2 triangles that meet the ASA condition, that there is a series of rigid transformations that's going to map one of those onto another. So that's our definition of congruent triangles. 2 triangles are congruent if and only if there's a series of rigid transformations that maps one perfectly on top of the other. And we definitely saw that with ASA. And by extension, that's also true because of, or angle side is also true. Because the 3 angles in a triangle have to add up to 180. If you know 2 triangles are congruent, you know the third one is. So angle side angle gives us angle side. One of the ways that the book said specifically we did not prove yet, and we're going to visit that later on in the textbook, is side, side, side. And then there was also side, angle, side. And then the final way actually requires a right triangle. So if you're asked to prove something with a flowchart proof, and you can see that you've got right triangles, you need to say that they're right triangles. That's part of the flowchart proof. But then if you can show that a pair of the hypotenuses are congruent and the corresponding leg is congruent, that also applies. So those are our 5 triangle congruence conditions. And then right next to it here is kind of a second part of this question. It says, what's the congruence condition used to establish these triangles, that these triangles are congruent, or these, there's a problem with my English here, I'm sorry. So if I look at this, I can see that I do have a pair of corresponding sides that are congruent, and you can also see that they're giving me that these angles up here are congruent to each other. And because we have those, we're close. The only thing that we need, and we have it because they share this common side, is we have an additional side. So if we look closely, right, what pattern's being met here is we definitely have this side and then this angle and then this side. And you can see the same thing here. We've got angle, side, and then angle, and then side. I think I just said that backwards, and I apologize for that. I need to be more careful. But it's definitely this side, and then this angle in between, and then the side. And you can see that over here, side, angle, side. So this is clearly the SAS is my justification for it. And then the triangles that are congruent, remember order matters, and it says here TGH on the one, and the one that goes perfectly with TGH is PGH. So it's congruent to triangle P and then G and then H. Write an equation of a line that is perpendicular to the line 4x plus 3y equals 12 and passes through the point 6, 12. Again, there's an error here. There is only one equation. Well, it depends if we're talking Euclidean or non-Euclidean geometry, but according to the parallel postulate, if you've got a line, right, and a point that's not on that line, there is only one line that goes through that point that's parallel to the original line. And I think by extension, it's true that if you've got a line and a point that's not on the line, there's exactly one line that's perpendicular to the given line that goes through the point. So that's what we're looking at here. I've got a particular line, right? This, for example, is the line that I have, and there's some other point that's not on the line, and I'm trying to find the equation of the line that is perpendicular to it that'll make this right angle. So that's what we're looking for here. So let's go ahead. First of all, I need to know the slope of this particular line. And it's not difficult to get that. I'm going to go ahead and rewrite this equation in slope-intercept form. So I'm going to take away 4x from each side. So this becomes 3y equals a negative 4x and then plus 12. And now if I divide everything by 3, I can see that y is negative 4/3 x, and 12 divided by 3 is 4. So I've got a slope that is negative 4/3. And if I'm trying to write the equation line that's perpendicular to this line, I'm going to have to use a slope that is equal to positive 3/4. So 3/4 is the slope that I'm looking for. Two ways I can do this. I can use point slope form of an equation, or I can plug into slope intercept form and solve for b. I'm going to do it both ways, I guess. So I'm going to start with point slope form. So again, I've got my variable y minus this y parameter, right? So it's y minus the y value that I know, which is 12 in this case. That's the y value that I know, equals my slope times the quantity x minus the x value that I know. And the x value that I know in this case is 6. So I can just go ahead and write everything down here. Y minus 12 equals my slope of 3/4 times the quantity of x minus 6. So if I use the distributive property and add 12 to both sides, I can change this to y equals, let's see, this would be 3/4 x minus 3 times 6 is 18/4, and then plus 12. So need to clean it up a little bit here in terms of these two numbers. So if I want to change, well, 18/4 I can reduce, right? 18/4, both of those are divisible by 2, 18 and 4. There's a common factor of 2 in each of those. So I can rewrite 18/4 as 9/2. So I've got negative 9/2. And I'm adding to that, I'm going to take the number 12 and I'm going to turn it into halves and write it as 24/2. And if I combine those, I'm looking at 24 minus 9, which is 15. So this becomes a positive 15/2, 15/2. So I think the equation of the line is y equals positive 3/4 x and then plus 15/2. Now, I want to probably check that by just go ahead and multiplying or adding, plugging in 6 for x and verify that it gives me 12. That's probably an important step. So let's do that. I'm going to erase this slope here, and I don't need this anymore either. So so I've got 3/4, and if I multiply that by 6, and then I add to that 15/2, I should get the number 12. 3 times 6 is 18, so this becomes 18/4, which I already know is 9/2. And when I add to that 15/2, hey, guess what I got? 9 plus 15 is 24/2, which is the number 12. So definitely this gave me 12. So that is the equation of the line, and that's me doing it using point slope form and then just modifying a little bit. I want to review the way that we've done it, since the beginning of the year, just to make sure that you don't forget that too, because I think either way's acceptable. I guess the question is which one's fastest for you. So think about them. Again, I know that your calc and pre-calc teachers would like you to know point slope form. But for the other method, we just start with this y equals mx and then plus b, the equation of line and slope intercept form. I'm going to plug in the x and y from the point I have in the slope that I need. Remember, the slope that I need was positive 3/4 because it has to be perpendicular. So I'll write down 12, that's my y, equals positive 3/4, and then times x, which is 6, whoops, and then plus b. Oh, that 6 got erased. So you can see this is the same path we've just been on. 3 times 6 is 18, so this becomes 18/4, and that equals 12. So I'm just going to be taking 12 and subtracting 18/4, which is 9/2. And when I turn 12 into 12 into halves, I get 24/2 minus 9/2, which is equal to 15/2. So that is my y-intercept. This is my slope. That's my y-intercept. So again, it's the same equation of the line. Question 3 had 4 problems. We're asked to simplify completely, and it says your answer may only contain positive exponents. So again, let's go ahead and take a look at these. I guess big picture, one of the things I see in part A is that there is a 2 that's not being raised to a power, and there's a 4 that's also not being raised to a power. So because of the commutative property of multiplication, I can definitely start out with this answer is going to have an 8 in it. Another thing that I can see is that there is a couple different terms, factors rather, with x in them. There's this factor, this, and then this one. So I've got x to the negative second and x to the positive fourth. So that most definitely is going to be x to the positive second power, right? Negative 2 plus 4 is going to be positive 2. And then the last thing that I see here is y to the negative fourth and y to the negative ninth. So I need to be careful here. That y, that becomes y to the negative 13th power. And I cannot leave this in my answer. So I can eliminate this negative exponent by multiplying by the number 1, right? So you can see exactly what happens here. These 13 factor, y to the negative 13th power becomes, in my denominator, y to the 13th power. And again, in the numerator, if you look at what we have, we've got y to the negative 13th times y to the 13th, which is y to the 0, which is 1. So there's just the 1 that's left behind. So let's go ahead and write our final answer here, and I'll clean this up. We've got an 8x squared, and then in my denominator, we've got y to the 13th power. And that's it. Let's go to B. On B, there's some parentheses here, things being raised to a power that we probably should, in one case, I think, deal with first, and in another case, deal with a negative exponent first. So let's actually take care of this thing first. I think this is a little bit of a problem for us. So we're going to deal with this 8 to the negative second power first. So the way I'm going to choose to deal with that is think, hey, this is 8 to the 8x rather to the negative second power. So this is just going to be equivalent to 1 over 8x to the second power. So the thing here is, and it's the same justification, same logic that we used in part A, I can migrate this 8x to the negative second, I can migrate those to the denominator, and it would become a positive exponent. So let's go ahead and, I guess we'll keep track of that. The other thing, though, that we have is we have 3 of these, right? This is to the 3rd power, and I'm going to go ahead and cube both parts of this, and then we'll deal with the y to the negative power, because there's going to be some y negative exponents. So 2 to the 3rd power is 8. So this is going to yield an 8 and then a y to the 6th power. And don't forget, we've got the thing I highlighted in yellow. It's going to be 8x, but that's being squared. And then finally, there's going to be negative 6th power, y to the negative 6th power, because negative 2 times 3 is negative 6. And then we're going to have a y to the 7th power. So definitely some cleaning up to do here. In my numerator, I've got 8, just plain old y, because x to the negative 6th and x to the 7th is just y. And the denominator, I've got 8 times 8, and I chose to write it like that, not 64, for a reason you'll see in a minute. And then I've got an x squared. The reason why I chose to write it as 8 times 8 is because these 2 factors of 8 make the number 1, so I can eliminate that from my final answer. So let's look at our final answer. Our final answer has, in the numerator, a single factor of y, and in the denominator, we've got an 8 and an x and a squared. So our answer is y over 8x squared. In part C, immediately I'm just thinking, you know what, let's just deal with this, right? I'm going to bring this 4x in parentheses to the negative 2nd power. I can write it out. I'm going to multiply by this giant 1 in parentheses 4x squared over 4x squared. And when I do that, you can see in my denominator I have this 4x, and over here this 4x, right? So it's a 4x to the negative 2nd and a 4x quantity to the positive 2nd, which is 4x to the 0 power, which again equals the number 1. So my entire denominator there is just simply the number 1 at this point. And my numerator, if you look at it, it's, let's not forget, there is a 4x squared, but then there's a 4x, the quantity squared. So let's let's write down what that becomes. So I've got my 4x squared, but then I've got 4x squared. If you're not looking at this, it's like, dude, you just said the same thing twice. But the difference is this is 4x times 4x. So if you look at it, there's 3 factors of 4 in my answer. 4 times 4 is 16, and I believe 16 times 4 is 64. And then I've got x squared, x to the third, x to the fourth, so x to the 4th power. So I've got 64x to the 4th power. And then finally, the final problem on this, for this final part for this problem is D. And on it, I'm immediately drawn to the fact that there is this, I don't know why I did that. There's this 3x being raised to the negative 2nd power. So it's at this point, it's a pretty simple fix. We've been down this road before. So we're going to rewrite this as a 1 over, there's a 3x in my denominator already, and I'm going to be putting down there a 3x to the 2nd power. And if you look at it, man, part C and D look awfully familiar. So what I have here is I have 3x in the denominator, and then there's there's another 3x and there's another 3x, right? Because I've got 3x and then I've got 3x quantity squared. So this is the part that was squared. So I've got 3 times 3 times 3, which is the number 27. Ooh, this is living in my denominator. Let's not forget. So it's 1 over 27x to the 3rd power. So there we go. That's part D. Okay, question 4 has 2 parts, parts A and B. Zoe was doing her homework when her dog was a bit off a piece of the paper, and she had left, all she had left of her sequence was the first and was term 1 and 5 shown here. So we know the first term is 96 and the 5th term is 486. The first question there is, could the sequence be arithmetic? So this question is essentially, if you have, let's think about what it would look like if this was arithmetic. So I would have a first term that had a value of 96, and then I'd go to a 2nd, 3rd, 4th, and a 5th term that would give me 486. So I need to grow by adding or subtracting the same value repeatedly if it's arithmetic, and because it's getting larger, I'd be adding the same thing. So I'm doing this in 1, 2, 3, 4 jumps. So how do I grow 96 up to 486 in 4 jumps? Well, really, this is a question of what would be the slope of a line that would go through these 2 points, or what would be the rate of increase if this was a function, right? And if I look at the slope, right, my change in y, or the change in my output divided by the change of input, would give me exactly the growth that I need. So let's consider that. So my change in y is going from 486, and I started at 96, so that's how much my output grew by. And my input values end up at 5, but they started at the number 1. So let's go ahead and just quickly, I apologize, I need to do a bit of arithmetic here. Whoops. So I'll take the 486, and I'm going to subtract from that 96. So I've got there 390, and I'm going to divide that by 4. And it gives me, okay, so it looks like my growth is 97 1/2. So each time I keep growing by 97 1/2. So I want to check this, right? So I'm going to start with 96 plus 97.5. So basically that should be my 2nd term. So let's write that down. So 193.5, 193.5. And then I'm going to add to that plus 97.5, and I get to 291, 291 plus 97.5. That lands me at 388.5, 388.5. And then finally, plus 97.5, please. Yep, exactly 486. So you know, if you wanted to, you could build the function by finding the 0th term. Well, actually, no. That's what the next question asks us. It asks us to do that. So find the explicit rule, right? So you give it a value of n, and it tells you exactly what the output should be. So in order for me to do that, I already have one of the big pieces. I've got the rate of growth. So I know that it's going to be 97.5 times n, because I'm adding 97.5 each time. So I'm showing that repeated addition using multiplication. So it's 97.5 times n, and then my 0th term, it's going to be some negative number, and I'm too weak mentally to know this. It's negative 1.5. 97.5 is, yeah, it's negative 1.5. So minus 1.5. And this is ugly, so let me erase that. So this should be my function right here. You can see the rate of growth in my 0th term also. So the other question here is, could this, so let me say yes, this could most definitely be a arithmetic sequence. And then the next question is, could this sequence be geometric? So geometric, you recall, means that we have a common ratio. So we're going to continue to multiply by the same thing each time. So if I start with the same kind of thinking I did with the previous part, I'll look at a table of value. This time I'm going to start with 96, but I'm going to be, my first term, rather, it has an output of 96, and then I've got my second, third, fourth, and I know the 5th term is 486. So in this case, instead of me adding the same thing each time, I'm going to multiply, 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 multiply. So I have to start with 96, and I continue to multiply by some number I don't know until I grow up to the value of 486. So I'm going to suggest, let's say that we're multiplying by b. So if you take a look at this, there's an equation here, right? It says start with 96, multiply it by b 4 times, right? Times b, times b, times b, times b. And when you're done, you will get a value of 486. So yeah, that's an equation, but you know, can we solve that? It's not as bad as it looks, and maybe it doesn't look bad to you, but let's get b to the 4th alone by dividing both sides by 96. So I'm going to take the 486 and divide by the number 96. And when I do that, I get 5.0625. So let's write this down anyways. So b to the 4th is 5.0 and then 625. Now, how can I solve that? let's come over here and just take a little think about something. So let's say that I told you that x to the 3rd power was the number 27. Now I know you know that I think it's 3 to the 3rd. 3 times 3 is 9, times 3 is 27. You know the answer is 3, but if we didn't know that, how would we do this? Well, may I suggest that we just use exponents. So consider the following. If I took the left-hand side and the right-hand side and I raised both of them to the 1/3 power, notice what happens over on the left-hand side. This becomes x to the 3 times 1/3, which is x to the 1st power. What? That's perfect, because that's exactly the same thing as x. Now over on the right hand side, what we have here is 27 to the 1/3, and if I take 27 and I raise that to the, let me grab the fraction template just because it's so much fun. Oh, wait a minute, I hit divided by. I need 27 and I need to raise it to the power of, and then I'm going to get the fraction template and I'll do 1/3 power. So 27 to the 1/3 power. Yeah, it's exactly what we thought it would be. It's the number 3. So this is great because now I have a mechanism for undoing raising values to different powers, right? Just raise it to the fractional power and it will undo that thing. So let's take a look at this. What I'm going to do here is I'm going to raise both sides of this expression to the 1/4 power. Let me get rid of this. I need the room, sorry. So if I do that, this is going to become b to the 4th to the 1/4 power equals 5.0625 to the 1/4 power. So b will very simply equal whatever that thing to the 1/4 power is. So let's look at that. So I've got 5.0625, and I want to raise that to the power of a fractional. I could put 0.25, but I'm here. Why not grab the cute little fraction template? No, that's not the fraction template. Geez, the cute little fraction template. I am. You know what? Let's put 0.25 there. 0.25, because that's a quarter, and I get 1.5. What? That's 1.5 is 3/2, right? So I just got a very nice thing that I could multiply by that would grow 96 into 486. In fact, well, yes, this could be geometric. And in fact, we can go ahead and fill in the missing terms, right? So let's take our 96 and multiply that times 3/2, or 1.5, and I get 144 is my, second term, times 3/2. Why am I doing it that way? I get the 216 times 3/2. 1.5 is the 324, and then of course the big question is times 3/2, 1.5. Do I get it? Yep, 486. So I can see here that I am multiplying repeatedly by 3/2. Now the final and the most difficult question is, what's the explicit rule for that? So I need to know the 0th term. And if I'm finding new terms by multiplying by 3/2, I'm going to have to divide by 3/2 to get the 0th term. So let's just write down 0th term here and get that. I'm going to take my 96, and instead of multiplying by 1.5, I'm going to divide by 1.5, or divide by 3/2, and I get a value of 64. So my 0th term is 64. So now I can write this down, right? This is going to be t of n is my 0th term, which was 64, times 3/2 raised to the n power. So again, all this does is if I put in n as 1, I guarantee you that's going to give me 96, right? Each time I'm multiplying by 3/2 times 3/2, and my 0th term is 64. So probably a little bit more of a question than we expected, but it was a good discussion, and I hope you really think about what we talked about in part B there. So in question 5, we're given 2 points. They're labeled A and B. A has the coordinates at -2, 11, and B is located at 12, 1, and we're asked to do 3 things with those points. First of all, we're asked to find the equation of the line that goes through those points. We're also asked to find how long the segment is from A to B. How long is it to travel from point A to point B? And then finally, we're asked to locate the midpoint of segment AB. So what's that location? What's that x-way spot where they meet with each other? So let's go ahead and start with the first one, find the equation of the line that goes through those 2 points. And of course, if I'm given a couple points and asked to find the equation of the line, my first thought is almost always, what is the slope of the line that goes through those two? So I'm going to identify the slope, and I write this because I often see that, we get in a hurry and I do the wrong thing, but it's going to be the change in my y values divided by the change in my x values. Here's my y values. I'm double underlining in green, and my x values I'll just single underline in blue. So I'm going to take in the numerator here, right? I'm going to take the ones in green, and I'm going to just go from the left to the right. So I'm going to take 11 minus 1. Let me just write that up there. It is 11 minus 1. So that's just the one to the other. That's the distance between those. And then my change in x, I'm going to go ahead and write as a -2 minus the number 12. So if I look at that slope, right, my change in y is 10 units and my change in x is negative 14 units. So this is my slope, and that can be reduced, right? There is a common factor there of the number 2. So this is 2 times 5, and then on my denominator I've got this negative 2, I guess, times 7. So if you look, there's this giant 1. So I've got this 1 times 5 in the numerator, so it's 5. And in my denominator, I've got a negative 1 times 7. So the slope is negative 5 over 7. Okay, now that we know the slope of the line that goes through those 2 points, we need to use that to identify the y-intercept. Now, in the notes that I did in class with you, I did this using point slope, but I'm going to go ahead and do this the way that we have done it quite a bit this year. I'm going to consider the equation of a line in y equals mx plus b form. Of course, there's 2 variables there. My variables are x and y, and there's 2 parameters. I've got my slope parameter and my y-intercept parameter. I already know one of my parameters. I know my slope parameter, so I'm just going to go ahead and write that in there, negative 5 over 7. What I'm trying to find out is my y-intercept parameter. So to do that, I'm going to pick one of the 2 points I'm given, and I guess I'll use the first one, and I'm going to plug in the y value from that point, so 11, that's the y from this point, and my x value from that point is negative 2, and then plus b. So if you look, what I've written down here is an equation. The only thing there is my y-intercept parameter, so I'm going to solve for that, and it's fairly straightforward. On the left-hand side, that's just 11. On the right-hand side, I have 10 sevenths, and then plus b. So to solve this, I've got 11 minus 10 sevenths plus b. 11 is 77 sevenths. I'm just taking that and multiplying 11 by 7 over 7 so that I have equal denominators there, and I'm going to subtract 10 sevenths. So finally I see that my parameter y-intercept is 67 over 7. Which is beautiful. It's a beautiful y-intercept. It's nothing wrong with that. So now I can write the equation of the line that goes through those 2 points. The equation is y equals, my slope parameter was negative 5 sevenths. I've got my other variable times x, and then plus my y-intercept was 67 over 7. So there we go, perfectly. The next thing I'm going to do is we're going to go ahead and find our the length of that segment. And there's a lot of ways we can do that, but I'm just going to go ahead and quickly sketch just a crude approximation of what this looks like. I'm going back to and somewhere up 11, so this is the point at negative 2 comma 11. And then I have this other point that's over 12 and up 1. So just roughly I get an idea of their relative locations. And what I want to do is, obviously, I'm trying to find the distance between these 2 points, right? I want to find the length of this segment from A to B. And to do that, I'm going to just consider a right triangle. Okay, so there's going to be, this is a vertical line that's just going to go down until I exactly meet the y value from my other point. And I'll just draw this one in green. It's just going to go across all the way to here. So in order to figure out the length of that red segment, it's the hypotenuse of that right triangle, I just need to know the length of the 2 legs. So the one that I've highlighted in this kind of orange color, that's the change in my y values. And you can see on the one hand, y is starting at 1 and it's going all the way up to 11. So 11 minus 1 is 10, so this leg is 10 units long. On the other one that I've highlighted in green, you can see x is starting way over here at negative 2, and it's traveling all the way over to positive 12. So if I do the subtraction there, 12 minus negative 2 gives me that this is 14 units long. Okay, so now I know the length of these 2 legs, so I can figure out the length of my hypotenuse. It's not bad. I'll call the hypotenuse, I guess, d, because it's the distance between these 2 points, and I'll just write that distance squared is 10 squared plus 14 squared, and that's just a statement of the Pythagorean Theorem. Therefore, I've got d squared is 100 plus, if I square 14, I get 196. Therefore, d is 296, I'm sorry, d squared. And then finally, if I take the square root of both sides, I get that d is the square root of 296. And if I write that as a decimal approximation, d is approximately, the distance between these 2 points is about 17.2 units. So make sure this is identified as my solution. And over here, I forgot to identify this as the solution. This is the equation, my line. Finally, the last thing that we're asked to do is locate the midpoint, the point between these 2 points. And you can see in that previous part, there's some point right in here, right? Some XY point that is exactly in the middle of those. And of course, our discussion, and when we looked at GeoGebra, we were talking about we're finding the average of our x's and the averages of our y's. So I guess I'll go ahead and write down. I'll write down the 2 points that we had. Right, we had this point -2, 11, and we have this other point that was at 12, 1. And if I want to find my x value for this location, right, it's going to equal, the x coordinate is going to be the average of my two x coordinates here. So I'm going to add -2 and 12, and I'm going to divide by 2. This is, of course, positive 10 over 2. So I can see that my x value is the number 5. And the other thing I can identify here is what is my y coordinate. So we'll do the same thing. We're going to find the average of my y's. So when I add 11 plus 1, that's giving me 12. I'll divide that by 2, so I have 12 over 2, which is the number 6. So we've got a location here. Our midpoint is located where x is 5 and y is 6. Are the triangles below congruent? If they are congruent, state the congruence condition and correctly complete the congruent statement. So if I just kind of think about these two triangles for a bit, of course, one of the things that I can add here is, because AG is a side that they both share, right? I can say that AG is congruent to itself by the reflexive property. So if I'm taking a look at it, I can go from this angle with 1 tick mark to the angle with 2 tick marks, and then to this one side that they share. So yeah, they're congruent. And in fact, that congruence condition that I just marked off was, I went from angle C over to angle A, or CAG. So angle, angle, and then the side AG. And so angle, angle, side is the congruence condition. And I can see that matches on the other side exactly, right? They share this angle, and then we've got the little angle right here. It's A on both sides, and then of course they both share this side down the middle. So it's definitely by angle, angle, side. And the final thing there is, what is the congruent statement for these triangles? So triangle G to C to A has to be congruent to triangle G to B to A. So triangle GCA is congruent to triangle GBA. And got it. Okay, a student believes that the triangles at right here up above are indeed congruent, and we're just helping them provide some of the missing statements and reasons to complete this flowchart proof. What I love about flowchart proofs is that, like a 2-column proof, they always contain both statements and reasons. So those things that are inside of the bubbles are statements, and these things that are written off to the side here are justifications. One of the advantages is that not only do I see those statements and reasons from a 2-column proof, but I also see how things are needed, how they flow together to create a bigger true statement, right? So the fact that at the bottom here I'm saying these triangles are going to be congruent by angle, side, angle congruence gives me some insight into what I should be attempting to do here. Certainly I need to show that I've got 2 pair of congruent angles, and the side that is in between those is also congruent, right? So that's what we're looking for. Well, when I look at the diagram, I can see that one of the things it says right above it is that it's given that point A is the midpoint of segment PT. So from P to T, this A is a midpoint. And right over here, I can say, oh, that I can see here's the statement, A is the midpoint of PT. So I can write, well, that's given. That is true. That's something that we're starting with. Now, as a result of that, because A is the midpoint of PT, it is the case that point A divides PT into two congruent segments. And in fact, the justification for that is the definition of this thing called the midpoint. So here's my statement. I can see I've already got this reason definition of a midpoint. My statement is that segment PA is congruent to statement TA. Right, these two pieces are congruent because A is the midpoint. The next thing that I have here is the insight is that my reason is vertical angles are congruent. Well, as I look at the diagram here, and I look at the two different triangles, the pair of angles that I think I would like to be congruent would be these ones. I'll mark with this green arc. And the reason why is if I had those, I would definitely have angle side angle. So as it turns out, those two angles that I just marked in green are indeed vertical angles. Now, angle A is a terrible name for that angle because there's multiple angles at that one vertex. So I have to understand the convention for naming angles. So what I'm going to write here is, for example, angle BAT, right? Angle B over to vertex A to T is congruent to angle, and I'm going to go F to A to P, F to A to P. So angle BAT is congruent to angle FAP, and that's because they are vertical angles. So I can see I've got a side here that is in between a pair of angles. I've got an angle pair, and the last thing I need is another pair of angles, and fortunately the diagram gives me them, right? You can see angle P and T are marked as congruent with tick marks. So I can just write that statement down, right? Angle P is congruent to angle T, and that's just given from my diagram. And then finally, now that I have everything I need, I can see I have the two angles and the included side, the side that connects those angles. I can write my triangle congruent statement, and that statement is that, for example, a triangle, I could say, I'll say triangle P to A to F. So triangle P, A, F is congruent to, and the order that I write the other one, it matters, right? It has to be in the same order. So if I go P to A to F, I'm going to have to say triangle TAB. So triangle TAB. So that is the completion of this proof. I've got all my statements and reasons from a traditional two-column proof, plus I see how certain things are requisite, they're necessary for me to say later statements. We are at question number 8, and we're asked to find both the perimeter and the area of this polygon below. And I guess we should probably take a moment and just talk about units here. So because units aren't clearly specified, this length, you can see that I'm drawing here from 10 to 11 near my x-axis. This is 1 unit. So when I talk about the perimeter, I'm going to be expressing it in those units. And when I talk about the area, right, it's a unit times a unit. So my area is going to be given in units to the second power, units squared, or square units. So part of this is easy, right? The perimeter, if I look at this, I'm just counting 1, 2, 3, 4, 5. I can see that B ends up at 6 and starts at 1. 6 minus 1 is 5. So this is certainly 5 units along on my perimeter. And I guess I'll use red to kind of keep these separate. So this is 5. And for segment AD, I can see it comes up to 7, but it starts at 1, and 7 minus 1 is 6, and I can count also 1, 2, 3, 4, 5, 6. The length of this segment is 6 units. This segment from B to C is a little problematic, right? Because it is this, it's a slanted one, it's diagonal, so I have to consider the Pythagorean theorem. And length B down to this point is 3 units long, and this is 4 units long. And this is a very nice Pythagorean triple, right? A 3, 4, 5, 3 squared plus 4 squared, we're looking at 9 plus 16, which is 25, and the square root of 25 is 5. So you can see I've got 6, 5, and 5, and the last bit of my perimeter is from segment C to D, and this looks like it's a little different. I'll go ahead and mark this here. This is 3 units, and then I'm going from 10 down to 1, or from 1 to 10. So this is 9 units long. So this segment from D to C, I'll just call it temporarily X, I guess. I'll call this X. That length is, I'll go ahead and write that 3 squared plus 9 squared is this length, X squared. So I've got 9 plus 81 is X squared. So it looks like X squared is 90. So that means that X, because we're dealing with this positive length of a segment, is the square root of 90. And I can write that in simplified radical form as 3 times the square root of 10. And as a decimal approximation, I don't even think I wrote that down. As a decimal approximation, I didn't write that down, and I don't have a calculator handy, so let's leave that like that. So let's put together our answer for the perimeter. The perimeter is 6 plus 5 plus another 5, and then plus 3 root 10. So we're looking at, what is that, 16 plus 3 root 10, 16 plus 3 times the square root of 10. And I did get that as a decimal approximation. That is approximately 25.5 what? 25.5 units. And again, what we're talking about here are the things that are this long, right? So they've got about 25.5 of those. All right, so let's talk about the area now. Area, there's a lot of ways that you can do this. I think when I did it in class, I might have done it by putting together some small pieces. I think I'm going to take this subtraction approach. So I'm going to make this larger rectangle that kind of goes around and connects all the way over to here. And if I look at this larger rectangle, it has dimensions from 7 to 1. It's from 6, right? This is 6 units along this direct dimension, and it's 9 units along this dimension. So my area certainly is going to start out with the product of 6 and 9, so I'll just write 9 times 6. But there's some things that we need to take away from that are not part of it. Namely, this is not part of my area. It's not part of this shape, so I need to subtract that. And this isn't part either. This needs to be taken away. So let's go ahead and figure out the area of those two things we need to subtract. So I'll do minus. The area of a triangle is 1/2 times base times height. So if I look at the small one up here that's near my 3, 4, 5, I can see I've got this 3 and this 4. So I'm going to have 1/2 times 4 times 3. So that's going to be taken away. And then I'm also going to subtract, if I look at these, this is a 3 and a 9. So I'm going to have 1/2 times 9 times 3. So we probably should do a bit of arithmetic now, right? 9 times 6 is 54. And I'm going to subtract from that 1/2 of 4, which is 2 times 3, which is 6. And I'm also going to subtract from that, let's see, 3 times 9 is 27. It's going to be, I'm going to take away 27 halves. 27 divided by 2 is like 13.5. So I've got 54 minus 6, which is 48, and then minus 13.5. Whoops, not 11.5, 13.5. And I wrote 11 twice. That's great. 13.5. So 48 minus 13.5, and we get an area. 48 minus 13.5. We're looking at 34.5. So the area of the polygon that's shaded in gray is equal to 34.5. And what are they? Those are those units being squared. These things, right? I've got 34.5 of those that occupy that area. So two parts, there's an A and a B. I don't know why the A didn't print here, but let's start with part A. As I look at this, I can say, oh, it's got some fractions, and I can pretty easily get rid of those fractions. So I am going to choose to multiply both sides of this equation by 6 times x over 1, right? I'm going to multiply both sides by 6x, and I'm going to push that factor of 6x all the way through across the equation. So I'm going to have 15 times 6x over 2 times x plus 7 times 6 times x over 3, and then that's going to equal 8 times 6 times x over 3. So now that I can see visually that I indeed did put a factor of 6 times x in every single one of those fractions, I'm going to kind of look at these and clean them up. So for example, the first term, 6 divided by 2 is 3, and x over x is equal to 1. So I end up with 15 times 3, which is 45. So that's nice. And then plus 6 divided by 3 is 2. So this becomes 7 times 2x, which is a nice little 14x. And then over on the other side of that equation, 6 divided by 3 is 2. So this is an 8 times 2x, which is equal to 16x. If I take away 14 x's from each side of this equation, we get that 45 is equal to, is it 2x? And then therefore x will equal 45 halves. So there's my answer, 45 over 2. And there's not a common factor there, so I'm just going to leave it exactly like that, 45 halves. On the other side, I know that the square root of 49 produces 7, right? So one thought is that I can say, well, since that's the case, I know that this 3x plus 12 must be equal to the 49, right? And I think we'll go with that, right? This thing inside 3x plus 12 needs to be 49 in order for it to have a value of 7 after I take the square root. So we'll stick with this approach. I'm going to subtract 12 from each side, and when I take away 12 units from each side of that equation, I get 49 minus 12 on this side. Isn't that cute? And then if I divide both sides by 3, oops, this side divided by 3 gives me x, and the other side divided by 3 is 49 minus 12 over 3. It's nice. It's true. I'm not doing any arithmetic at all. I guess I should do that at 49. I'm embarrassed to say that. Maybe I'm tired. I'm grabbing my calculator when I shouldn't. 49 minus 12 is exactly 37. And I guess I'll just write this as 37 thirds. There's no common factors there, so my answer is 37 thirds. And it's always nice to, take an answer like that and check it. So if I was to look at what is the square root of 3 times 37 thirds plus 12, well, 3 times 37 thirds is 37. So this is a square root of 37 plus 12. Not 2, 37 plus 12. And when I add 37 and 12, I do get 49, and the square root of that is 7. So this does indeed check. It produces a value of 7. Give the best description of the polygon bound by the following equations, including the special properties and the perimeter of the polygon that you find. So as I look at these, I think 3 of them look like they're going to be fairly straightforward to graph, right? The one that I think would take just a bit more concentration is perhaps this third one, but I think I'll use a different color for each one. So I'll start with this top one, and I think I'll use green. Let me select a beautiful green. And we'll just rewrite this. This is going to become y equals the opposite of x plus the number 4. So I've got a y-intercept of 4, and I have this slope pattern of -1/1. So this is pretty straightforward, right? These are all going to be points on it. Let me grab a ruler here and line this up. So these points, right, form the first boundary of this polygon. So there's one line. Let's take a look at the next one. The next one, let's see, I'm going to add 3x to both sides. So y is equal to 3x and then -8, right, 3x minus 8. So one of the things is like, oh shucks, I don't see where I can plot the y-intercept right there because -8 is not visible. And rather than trying to extend this graph and try to estimate that, look, let's just pick some different values of x and see what we get. So for example, if I pick x as 4, right, I could do a quick little table of values. If x is 4, all of a sudden this becomes 3 times 4, which is 12, and 12 minus 8 is 4. So y would be 4 also, right? 12 minus 8 is 4. Well, that's a fabulous point, right? 4 is one of the points on there. I could do another one, like if I said x was, for example, 5, then I'd have 3 times 5, which is 15. And if I grab the 15 and I subtract 8 from that, we're looking at exactly the number 7. So 5 goes to 7. And I can see that slope pattern of up 3/1, right? So I can go down 3, back 1, down 3, and back 1. So this is my next boundary for this problem. Let's grab our ruler and line this up. And we're looking at something like this. I can spend too much time doing this too, but I'll just go ahead and draw a line through there. All right. So let's skip the one that I put a star by and graph the last one there. All right, y is equal to the opposite of x plus 8. So this is like that first equation, right? So this time I've got a y-intercept that is way up at 8, and I've got the exact same slope, right? Down 1/1, down 1/1, down 1. So those are all those points. We can line up our ruler there, and just go ahead and draw the line that goes through those points. And then this final equation is the one that I've been putting off, and it's time to do it. I think I need another color. Let's go with this. I guess this color blue. So let me go ahead and write this down here. This is it's going to be 3y equals a positive x minus 8. Okay. So now I'm going to go ahead and divide everything by 3. So y will equal 1/3 x minus 8/3. And I can see that's that's maybe the challenge. So let's see if we can find some values of x that produce integer outputs, perhaps. So for example, if I try a number like I don't know, I'm just guessing. Let's try -1. So if x is -1, then I would have 1/3 times -1, which would be a -1/3, and then minus 8/3. Oh, this is beautiful, because -1 and minus 8 is -9/3, which is the number negative, what is that? -3? No, it's -9/3, which is -3. So when x is -1, y would be right here at -3, and I just have that point on the graph. Let's use the slope pattern and then check and see if this next one works. So if the slope is up 1/3, so this should be a point that works nicely also, right? So let's go ahead and put x as 2 into this equation. If I put x as 2 in it, this becomes 2/3 minus 8/3. And yeah, 2 minus 8/3 is negative 6/3, which is exactly negative 2. So that is definitely one of the points. So up 1/3. I might check one more. If I put in 5, I think I'll just erase this too. If I put in 5, it becomes 5/3. And 5/3 minus 8/3 is negative 3/3, which is exactly negative 1, and that's the point I plotted. So pretty confident that this is our third and final line. So I'm just going to go ahead and grab the ruler here, line it up, and draw this line as well. That's pretty accurate. So when I look at it, appears to be I would say at least a trapezoid, right? Because these two lines are parallel to each other. They had identical slopes. In fact, these things have slope of -1, and this had a slope of -1. So this slope of -1 is definitely telling me that those two lines are parallel to each other. So it is definitely a trapezoid. The other thing that's happening is if you consider the other two sides, if I look at this, this has this, if I wanted to figure out the length of this side of the trapezoid, this is a 3 and that's a 1. So if I'm looking at that small right triangle, right, the length of this length from here to here would be 3 squared plus 1 squared. So we're looking at 9 plus 1, or 10. So this is the square root of 10. And the reason why that's interesting to me is it turns out, if I look at this segment here, and by the way, if I go up 1/3, it is without a doubt that blue line is supposed to be right there. So if I just follow that slope pattern up 1/3, so my graph is off. But this is a 1 and this is a 3. So I have the same thing, right? 3 squared plus 1 squared is 10, and the square root of 10 is how long this is. So this is not just a trapezoid, it's an isosceles trapezoid. So I've added a couple summary items here. If I was to call this just randomly, I assign this A, and I assign this vertex B, and I assign this C, and I assign this D. I've pointed out that AB and DC both are the square root of 10, so AB is congruent to DC. So I could put these congruent tick marks on that because they both equal root 10. Also, the slope of AD and BC are equal to each other, so I know that AD is parallel to BC. And then my final response here is parallel or quadrilateral ABCD is an isosceles trapezoid. Segment AB is congruent rather to segment DC, because both AB and DC have a length of root 10. Line AD and line BC both have slopes of -1, so those lines are parallel, and those two sides, right, side AD and BC are parts of those lines, so they're parallel as well. So this is definitely an isosceles trapezoid. Okay, the final question on the study team